You hear me? All right. Well, I think we're going to go ahead and get started, if everybody's game. Smart cards are a pretty interesting topic by the looks of the attendance here. So this is Java Card 101. It's really about half smart cards, half Java card. How many people here have actually been part of a smart card deployment of any sort, shape? That's about right, I guess. One. All right, good. Smart cards are kind of boring, you know, in all fairness. I've been doing them for a couple of years. And it's not the most compelling topic in the planet, although it's real easy to screw up. And when you don't pay attention to something that's boring, you'll shoot yourself right in the foot down the road. So if you are thinking about doing a smart card deployment, you know, try and stay on board. I'm going to run through a lot of these issues, and you're more than welcome to come up afterwards and talk. I've got a lot of opinions that didn't make it into this thing. A couple of things before I start. One, I like to preface all my talks by saying, don't believe anything that I say. We're at Black Hat, you know, we're security professionals and get paid to be paranoid. So by all means, don't trust what I'm saying, challenge me. If you disagree or know better, call me on it. I'd much rather have people walk out of here in a rage because I've said something they disagree with than to everyone nod and walk out the door. Secondarily, when dealing with smart cards, I like to talk about security in the sense of, you know, Maslow's pyramid of human needs, but we have Maslow's pyramid of, you know, security needs. You have to have your firewall figured out and configured properly. You have to have operational practices in place. You have to be able to respond to incidences before you can do higher order things like deploy an IDS. You know, people have IDSs that just sit idle because they don't have the time or the people or the procedures to deal with it. Smart cards are the same kind of thing. They look real sexy and all, but in all fairness, you better have your bases covered before you start going in the realm of why you need to use smart cards. So on that note, why do you care about this talk and why do you care that I'm speaking to you? I've been doing Java card security for about 3 years off and on. I work for a company called Cigital. It's like digital with a C and possibly the worst name imaginable to name a company. We're based out of Dulles, Virginia, which is about 40 miles outside of DC. I've done a lot of other security stuff, founded the Shmoo group of security professionals who have any number of projects. Why do you care about smart cards? It's a great question. After 9/11, obviously security, you know, everyone became more concerned about security, or at least that was kind of the common conception, is that was what was going to happen. It turns out right now the only people who really seemed a lot more caring is the government. And that's really reflected in what we're seeing today in smart card deployments. By far the largest smart card deployment ongoing today is the US federal government, who's deploying about 11,000 smart cards a day. That makes American Express look like child's play. So these guys are really pushing out a lot, but they're the only ones really in the space who have started to kind of get traction with smart cards. 10 years ago, when people sat around and talked about smart cards, we said, hey, you know, everyone's going to have one in their wallet in 10 years. How many people have a smart card in their wallet right now? Wow, that's actually better than I thought they do. How many of those have been issued by your employer? Excuse me? Well, fair enough. Wow, that was good. I think we're starting to see the time when smart cards are going to become required to do a lot of different activities in our day-to-day life. Up until this point, there just hasn't been really that level of risk required to deploy a secure token like a smart card. And secondarily, the technology hasn't existed to allow medium and small-scale businesses to get into the mode of actually deploying smart cards. Up until recently, it's been a fairly expensive process to do, even you know, especially a small-scale deployment. And you know, it's going to be 6 o'clock at the end of this thing, and drinking will ensue. So try and stay with. I think the study says your average attention span is 40 minutes. So we're going to try and double it here, and we're going to try and double it in Vegas right before we get drunk. So if you need to jump up, you know, do jumping jacks, whatever it takes to stay awake. Throw stuff at me. I'm really, you know, with you know the 8 people we have here, it'll be fine. So what is a smart card? Originally there were these mag stripe cards. I think everyone's got one of those in their wallet. They have a magnetic strip across the back. It looks like a credit card, pretty much is a credit card. You can encode information on this stripe. There's low density and high density stripes, but really we're not talking megabytes and megabytes of data. It's a very finite amount of data you can store. In general, it's static, and it can be copied readily, especially the low density cards. There are copiers that you can buy, you know, publicly on the internet to just copy low density mag stripe cards. So the idea of a smart card was developed to provide kind of a secure computing and storage platform to allow for more advanced portable technologies or portable storage technologies. It's defined by ISO 7816 if you get bored enough to read the spec. The spec's actually interesting in some sense because it specifies a lot of physical characteristics about a smart card, like how much you can bend it each way before the chip can pop out, how many times you can bend it a certain amount before the chip comes loose. So you actually have to do all these really, these stress tests according to ISO in order to have a real smart card. They also now have punch-outs. Like there's the standard magstripe format smart card, but there's also ones now that have little punch-outs, which you commonly see loaded in like a GSM phone, where you take this, basically still the same contact for the smart card, but you plug it into a phone, and now you have a little tiny portable token as opposed to the big one that's on the card. There's a lot of other specifications that kind of deal with smart cards. I'll talk about a lot of them today. The one I'm not going to touch on is EMV, which is EuroPay, MasterCard, and Visa. As you can guess, this is a specification that deals with financial processes and storing of financial data on a smart card. EMV governs a lot of the financial space for smart cards. It's not a memory card. This is something that's kind of important to keep in mind. Smart cards do processing. They actually have a microchip on them that's capable of thinking, doing a little bit of work. A memory card is effectively just a portable storage mechanism. Looks like a smart card, has the same contacts, but internally it's really pretty dumb. Smart cards receive clock and power from an external source. This is really important. They operate usually at 5 megahertz and 5 volts, I think. But that's all supplied by the terminal. So as an attacker, you have access to, say, manipulate a terminal, and you can underclock or overclock and undervolt and overvolt a card. And I'll get into some attacks in a minute as to why that becomes important. There's contact cards where the typical smart card where you have the little pins and they'll contact the card and transmit data and supply clock. You also have contactless cards that basically you move it through a magnetic field, it induces a current onto the card, and allows the transmitter to transmit data back to the terminal. Those aren't as common anymore as the standard contact-based cards. There's 3 types of memory on a smart card, and this is actually important as an application developer or someone deploying them or integrating them. There's ROM, typical read-only memory. There's EPROMs, which allow for basically persistent memory to be made persistent across power loss. Standard EPROM mode, I pull power, but it still is going to be the same thing next time I plug it in. The problem with EPROM is it's a little slow compared to something like RAM. Secondarily, you get a finite number of writes on it before you've basically exhausted the EPROM's ability to store data, usually about 100,000 writes or so. So EPROM space needs to be used wisely, as opposed to RAM, which is just kind of your standard run-of-the-mill, use it and abuse it kind of deal. The memory amounts that I quote here are kind of state-of-the-art for today's smart cards. 5 years ago, these numbers were probably an eighth of what they were now. Think about trying to jam an application into, a grand total of 30 some odd kilobytes, like a whole full-blown application. It's real tough. Smart cards that exist today give you a lot more flexibility. 32 plus 8, 40 kilobytes of memory is still not a lot to play with, but it's a lot more than it used to be. But of course, we'll never need more than 640K. So when we're talking about smart cards and the attacks against them, we'll be talking about some different entities. There's, of course, the terminal, which contains kind of the off-card application, off-card logic to talk to the card. There's the reader, which is the physical interface to the card itself. And sometimes the reader's attached, like part of the terminal, and sometimes it's not. If for your PC, for example, you may get a smart card reader that's, hangs off a USB dongle or something like that. That's just a standalone reader, and the terminal effectively in this case is your PC. There are smart readers and dumb readers, and when you're doing development or testing the smart cards, it's really important to know the difference. Smart readers, effectively, you tell the reader what you want it to do. You say, I want to tell the card to do this. And then the reader kind of mediates the thing and says, oh, well, it's this type of card, so I'm going to communicate it like this. And it abstracts a lot of nuances from different cards from you by having some intelligence. Dumb readers are basically, RS-232 to smart card converters. You send it some ones and zeros, and it converts the ones and zeros to the right frequency and voltage, and then drops them on the card. Real dumb. You can get dumb card readers for about $10 a pop. You can get like the smarter ones for about 50. And of course, there's the card. But beyond that, there are a herd of people you need to be concerned with. There's some people who write the applications that live on cards, which may be different than the card issuers. For instance, for an Amex Blue card, Amex may be the issuer of the card, but you may have a Hertz rental agency loyalty application that lives on it. Hertz has written the application, but Amex is the one who's ultimately responsible for that card. And of course, there's the card holder, the person who has the card. And there's obviously a lot of noise. So what do people do with smart cards? Well, the one people like to think about is stored value because it's real attractive to hack into a stored value system. This is basically where the card says, hey, I have $20. And by I have $20 mean what's on this card is worth $20. And so what I'm capable of doing at that point is putting it in, say, a vending machine, and the vending machine says, oh, you want to buy a Coke? That'll be $1. And the stored value card says, okay, well, decrement me by $1, and I'm now down to $19. If you can subvert that system, you've won. I mean, you've won the ultimate victory of printing money. There's no treasury to be concerned about. You're just able to basically create your own cash. There are a lot of other applications for smart cards. Amex's big rant for a while was the idea of a wallet where all your information, your sizes, the colors of your clothing, all this crap would just be stored in the card, and you would never have to, you'd walk into a store and say, I need a suit, and you'd hand them your card, and it would have your neck size and everything, and 5 minutes later they'd have it tailored rather than putting it on your body and you walk out the door. That's not really happening yet, but it's an ideal that a lot of people are gunning for. Loyalty applications, keeping track of frequent flyer miles, things like that. And then identity and access control, biggies, big ones for the people in this room. Who are you and what are you allowed to do? The card may contain information that proves who you are, and it may even contain information that says what you're allowed access to. Remember, this is just a token and it can be stolen, so when designing smart card systems, we'll get into that in a minute, you need to be concerned about what happens when the card leaves the card holder's hand and goes into an attacker's hand. And also just generally secure storage. You want to store some RSA keys and put them in your server so they're never actually disclosed to the operating system, put them on a smart card. So what happens when you actually want to converse with a smart card? Smart cards are command response based. They're not the most glorious pieces of computing equipment. You basically ask it a question, tell it to do something, give it a command, and it will respond. In general, it's not thinking about things in between commands. Like you tell it a command, it does this thing and it responds, and then the smart card just kind of sits there idle waiting for you to do something else. It's not going to go out and run SETI at home, in its spare time. The basic packet you can think of for smart cards is called an app-do, and this is defined by another esoteric ISO spec, that's a lot better. There's also lower level encoding that you need to be aware of. There's T equals 1, which is basically a byte or T equals 0, it's a byte oriented, like I send 10 10 10, and that's what you get on the other side. T equals 1 is a more advanced protocol that cards can use to communicate, which basically allows packetized data to be sent, so multiple sessions can be running to the card at one time, so the card can be kind of doing multiple things at once. If you put it in the reader and 3 different applications in the terminal want to interact with you at a given moment, they can all start a concurrent session through a T equals 1 session. From my experience, what I've seen about half the cards that are made today that you can buy from most companies are T equals 0 and the other half are T equals 1. There's really no particular reason to have T equals 1 cards unless you're going to be running a very sophisticated system. Finally, another thing you need to be aware of, there's this thing called answer to reset. When you plug in the card and it first gets power, it just spews forth information. It says, hey, I'm going to use T equals 0 and I expect this kind of voltage and this is my data rate and a bunch of other crap. And you can decode this answer to reset. The really important thing about the ATR is understanding that's where you're going to find out which protocol you're using. So bear with, there's only 200 slides that are in the dregs and this will get interesting, but you got to understand this stuff to move forward. This is the basic breakdown of a command app-do. Class instruction, P1 and P2, you just think of it as an opcode, kind of a hierarchical of a class of instructions. So you might have like 80 as the byte for your class representing encrypted and 00 representing unencrypted. And then you have a whole series of instructions within that class. And then you have these parameters you can modify to basically cause those instructions to do different things. And then you can, that's what's required. If you just have that information, it's called a case 1 app-do. Again, if you leave this room and decide smart cards are so compelling that you've got to go look on Google and figure out how to do this stuff, you'll see these phrases again, and that's why I'm kind of bringing them up right now. Secondly, if you decide you want to send data to the card for some reason, you're going to set this thing called the LC, which is a byte that says how much data you're going to send, and there's this data payload. And then there's this thing called an LE, which is basically how much data you expect to get back. So if I'm telling you I'm going to load this data and I don't expect anything back, I'll give you an LC and some data and I'll leave off the LE, and then the card should just respond with everything's A-OK. So the response app-do, basically this is what the card sends back to you. If you set the LE on the previous, on the command app-do, it'll send you that much data back. And then the status word, which you can think of like an exit code. The status word could mean A-OK, or it could mean I have more data for you. You only asked me for 20 bytes, but I really have 30 bytes, so why don't you ask again and I'll give you the last 10. Or it could just mean some kind of error condition occurred. So like in Java card, if you throw an exception and the exception is caught, the exception will come across in the data and you'll get then a status word to indicate there was an exception. So just to be clear on this, using smart cards doesn't mean you're secure. I may be preaching to the choir, but my day job is being a security consultant, and too many times I go in the field and people think they found the silver bullet, Excalibur, whatever, that makes them secure. I use SSL, so I'm secure. This is the way it goes in application security right now, and that's not the case. The same is said with smart cards. Just because you are using a smart card in whatever your authentication system doesn't mean your authentication system is secure. You can easily shoot yourself in the foot and probably make a bigger hole in the system than you originally had. Some common attacks against smart cards are actually very interesting and kind of fun to play with if you have the capability. And by capability, I mean if you're in college and you have access to a double E lab, you can pull off anything I'm going to show you here. Glitching is basically the idea of trying to induce an error onto the card through some mechanism. You have control of clock and you have control of power. So you increase one or decrease the other, whatever it takes. The card, in theory, should recognize, hey, I'm in an overvolt situation, or hey, I'm being underclocked. Someone's trying to do something malicious to me, and basically stop activity. The problem is especially when you overvolt and underclock a card, they tend to kind of lose their brains. It's not really in its operating environment anymore, and it may get kind of pissed off. And that's really what you're hoping for when you're attacked with a glitch. You're trying to squeeze out of that card some kind of information it normally wouldn't disclose. Best case scenario, it just starts at byte 0 and dumps all its memory because it's got nothing better to do. That doesn't happen very often anymore, but some of the older smart cards you could glitch and they would basically just, boom, here, have everything. All my secrets, all my code, everything you ever wanted to know. Cards are getting better. The hardware is getting better at overcoming, basic glitch attacks. So people have become far more sophisticated. Paul Kocher and his crew at Cryptography Research, I think, go to cryptography.com. They got a lot of papers on this thing called differential power analysis. DPA is kind of an extension of differential cryptanalysis, where I get a whole pile of ciphertext, and using statistical analysis, I'm able to kind of work my way backwards through the protocol and find out interesting things that have occurred and potentially get the key. Differential cryptanalysis was kind of one of the primary tools cryptanalysts were using when they were trying to attack various AES candidates. Rindall, the closest way that Rindall came to get broken before it became AES was differential cryptanalysis, but they could only get about 2 rounds back into the process. Differential power analysis, on the other hand, basically looks at the physical manifestation of the encryption process. When you're doing DES and you're running through the S boxes, every time you go through an S box, it's drawing power because it has to do these massive computations. And so you can watch that power draw, and you see this little wave of, this thing drawing power, and then it'll dip, and then it'll pop back up, and you'll see 16 of these things as it goes through an S box. If you are able to statistically analyze those 16 over a whole series of ciphertext that's spewing out, you can work your way backwards and find the plain text, you can find the key, you can find all this stuff. Kocher and his crew were so good at this that for a while they were kind of barred from basically doing any security work on smart cards. When they started doing this research, they hammered every smart card they got their hand on. It was just devastating to watch what they were able to do to the smart card industry. So what ended up happening is the engineers who developed smart cards had to go back and find ways to basically mask this power draw, trying to get the card to do other things or do things out of order in an attempt to kind of suppress it so you couldn't do reasonable statistical analysis. They've gotten better, but a lot of cards you see in the market are still going to be susceptible, at least in some part, to DPA. Then, of course, there's Ross Anderson's work. Ross Anderson wrote Security Engineering, which I don't care what you do in the security realm or how seasoned you are, I highly recommend picking up that book. It is just an impressive book about building secure systems from soup to nuts. He focused largely on low-cost attacks against these tamper-resistant devices, i.e. smart cards. Things like inducing errors in the thing with a light bulb. Basically, you hammer the chip with photons, energy, and some of that energy is going to work its way into the card and eventually cause some error somewhere in there. And if you do this at a slow enough rate and are able to induce it, maybe something interesting will happen. There was a story a few weeks ago that hit Slashdot and all the wires about people doing this on main memory and computers and things, putting a light bulb inside of a server and it causing it to do all kinds of nonsense. Same kind of deal. Excuse me, the nachos are killing me. You can also use things like laser cutters and microprobes to actually get into the chip on the card and change data, or tap it at least. You know, you can get to a line and you can tap a bus, and you can see what that bus is spewing forth. That's kind of a neat attack. And then finally, there's this idea, you can actually just shave the damn thing. You can take the chip off, put it in a harness, and you can just peel off a couple microns at a time and take pictures of it. And there's software out there that allows you to take pictures and allows you to reconstruct not only the structure of the chip itself, but you can also determine, if you know how the EEPROM's constructed, what's a 1 and what's a 0. And even with RAM, if it's used enough, you'll be able to tell what its normal value is. So you're able to shave this memory over and over and over until you've made this three-dimensional map of the chip. In response to these types of attacks, what the chip manufacturers have done is basically scrambled the hell out of these chips. They'll take EEPROMs and they'll take some addresses and put them up here, and then they'll put some down here, and they'll put some way over here, and then run connections all through the silicon. I mean, it's just a mess. But it's still, if with reasonable equipment and reasonable software, you can still reconstruct how the chip has been assembled, and then make a logical map of how this thing's created, and then figure out what the bit values were. So that's attacks against the card, and those are really sexy and all, but 9 times out of 10, you don't need to resort to that because the system end-to-end is really generally broken. For most people that are kind of homebrewing their own smart card solutions, and even people who are doing this professionally, the card ends up not being the weak point so much as the protocols that they're involving or the kind of backdoors or side channels that they put into the system. One of the biggest ones is just simply, you look at the protocol, you watch what's going back and forth across to the card, and you're able to say, hey, look, all it's doing is asking the card, did you decrement that by $1? And the card said yes. All you need to do at that point is create a card that just says yes every time someone asks if it took away money, and you have an eternal source of cash. It's an excellent attack. The guys at MIT, God help you if you ever install a high-tech vending device at MIT. There's just this history of shattering these things into pieces. I tried to find a URL for this, but I couldn't. But these MIT guys basically, they put these vending machines in the freaking MIT labs that had smart card stored value things to get sodas and stuff. So these guys took credit cards. They put, you can get conductive ink from Radio Shack, and then Frankensteined up an RS-232 cable and wrote a driver, and then they sniffed what was happening on the card for a while, and then they were able to take their thing and just walk up, plug it in, they'd reproduce the protocol and software, and they could get free food forever as long as they were at MIT. There was a Blackboard, this company called Blackboard that makes an ID system for universities. They had some big hemorrhage recently where someone basically reverse engineered their protocol. The problem today is reverse engineering equals DMCA lawsuits. So there's some concern about people's willingness to get involved in this, but I find that once you go to college, you don't really care about getting sued, you don't really care about going to jail, you just care about impressing people. So never underestimate the power of a bored college student. That person is your worst adversary if they don't like you or they want free ramen. So, and then finally, some of these systems I've seen, they actually, okay, so you got the smart card, this fully robust protocol and all this stuff, and then, just in case the smart card reader isn't working, there's a mag stripe on the back that just basically has your name encoded. So okay, smart card reader doesn't work, slide it through the mag stripe, bing, door opens and you walk through. Be aware of any of these systems that have these other alternative access mechanisms because they'll probably be the weak point. So Java cards, after all that, I'm sure you're still really gung-ho to deploy smart card systems, but nonetheless, I'm going to plow forward. Back in the day, here's this 27-year-old kid standing on the podium saying back in the day, cards were really difficult to make. The program that made a card basically went into a hardware mask. The code was created in a piece of silicon, and then they made thousands of these things. And if there was a mistake found after fabrication, you had to basically take all the old cards, dispose of them, and then go through the whole process again. That's like the worst case software engineering problem imaginable. Like, oh, you screwed up today. We won't find out for 2 years, and it'll cost us, $2 million to redo the whole project. Excellent. That concept and that problem with smart cards made them really difficult for people to bite on for years. And that's why generally people are just using smart cards as memory cards. Here I'm going to store some data and I'm going to get it off it, and that's all it's going to do. With the advent of things like Java Card, you've got more of a general purpose operating system on the card, and you're able to actually load your own applications. Good God. You're able to load your own applications, make your own code. If it doesn't work, you just delete it and you put new code on. It's a marvelous thing. So there's a lot of things you can do with this now, and it puts smart card technology in the hands of mortals as opposed to governments. You talk about adversaries as, you've got adversaries like a small company, you got adversaries like IBM, and then large governments like the US. Well, this is the same kind of deal where before only the large adversaries could handle this, and now it's much more reasonable. At the end, I've got prices and whatnot from various vendors to give you an idea of how inexpensive this really is. So Java Card is a really, 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 really stripped down version of Java. For those who are familiar with the Java heritage, there's J2EE, SE, ME, and then way down at the bottom, there's Java Card. It is seriously small, and it's got to fit in the 64K on these new cards. Yeah, this is not important. So here's the API. Basically, the API is broken down into these 4 sections. Java.lang. Note, there's no double, there's no long, there's no cars. I mean, just a lot of things you would expect to see in Java, don't exist in Java Card because there's not as much processing power, there's not as much storage. Hell, integers are optional. Some vendors actually implement it and some don't, and you have to bootstrap in. And you remember in CS class when you had you don't have a processor that can process doubles, so you got to figure out how to do it with a couple of integers or whatever. It's the same deal. You're playing these asinine tricks with shorts to try and represent integers. Java Card.framework basically gives you methods to handle parsing of the appdos, gives you mechanisms to interface with PIN, so you don't need to reinvent the PIN mechanism. Thank God. I fear what would happen if the people who are deploying Java Card systems had to reinvent how to do a PIN. You want to see a software engineer screw up, that would be a great place. So at least that's there for you. And then it's JC system, which basically gives you interaction with kind of the low-level parts of with Java Card. Java Card security, as you can imagine, security equals crypto, except it's not the crypto actual activities, but the storage of keys and the creation of random data. And then there's a Java Card x.crypto. X, I think, means it's export controlled, and that actually is where you'll find your DES and AES and RSA algorithms implemented. So the Java Card virtual machine is, it's not really a virtual machine so much as machines plural. There's actually part of the Java Card virtual machine that runs off the card. This is where it gets exciting. The converter, basically, when you create the applet that gets loaded onto the card, the bytecode is verified off card. So you create a static file, and then you verify it, and you write it to disk, and hope to God nobody modifies it before it lands back on the card. This is a pretty core problem with Java Card, and the reason a lot of other specifications exist is to make up for this problem. It's really expensive to do standard Java bytecode runtime verification. I mean, really expensive on even a standard PC. You've all seen how big Java processes get, right? This has got to fit in substantially less memory. There are companies, namely there's one in France that's working on doing some kind of more advanced runtime verification, but I wouldn't expect to see that in the public domain for probably 3 or 4 years. This thing also initializes variables, and ultimately you end up with this thing called a cat file, which for all intents is a jar file, and by all intents, you can use jar utilities to disassemble the things. That's what it looks like. It's really been optimized. It's small. It'll take a lot of Java code and crunch it right down. Then there's an on-card installer to get the applet actually loaded on the card and instantiated, and then there's an interpreter, the standard issue Java interpreter that actually runs the bytecode on the card. It has very limited garbage collection. That's a pretty new thing. It used to have none. So you would get into these weird situations where you'd chew up memory because you could never really get rid of objects. Now they're realizing that's not such a good thing. So here's the way it flows. You create a class file, you run it through the converter, it creates the cat file, then you have a reader/terminal, it goes into the installer and then gets made an applet. I find visuals help, especially because I haven't had any, and I'm pre-assuming you all know what a smart card looks like, because you note there hasn't been one in the whole presentation yet. It's because my mad Visio foo did not allow me to create something that looked even close to a smart card, so sorry. So then there's the JCRE. This you can think of as the actual operating system that you're interfacing with on the smart card. What's really odd about the JCRE is the lifetime of the runtime environment in Java Card is the lifetime of the card. On a PC, you're used to basically, if you're familiar with the Java architecture, you'll bring up a runtime and you'll do a bunch of stuff, but you can tear it back down and then you bring it back up and tear it back down. And you do this over and over and over. On the card, you don't have that option. Once you decide to terminate the JCRE, effectively the card is dead and will never reply to you again. So this is really the operating system of the card. In general, when you get an applet on the card, you'll only instantiate that applet once, unless you have a damn good reason to have to instantiate it multiple times. That's kind of hairy in spots, but there are other specs that will help you deal with instantiation issues. All this basically, the runtime environment remains constant between power on and power off, or power off and power on. The runtime is just there. It's doing its thing. You pull out the card, you put the card back in, the card remembers exactly where it was, and then it basically brings itself back online and is ready to start processing things again. It is a subset of the JRE, as you can imagine, but it's got extra things, so it's not technically a subset. It's got some extra things in there to help protect your applet from that hostile environment that it's living in, namely your pocket or the reader. So it handles command processing. Basically, when you send a command to the card, it's not your applet that gets it first. The JCRE actually gets it ahead of time and looks and makes sure everything's hunky-dory and then punts it off to your applet. It handles transient objects. So if you want to do something rapidly or you want to have something in non-permanent memory, you can have it in RAM. So that way, if it's a key or some kind of crypto manipulation, you punt it off and you do it all in RAM. And that way, when you pull power from the card, you're not able to go back in and figure out what the hell you were doing. It also provides a mechanism for transactions. So if you're doing something that's particularly sensitive, like decrementing the stored value counter, you can basically wrap it in a transaction handler and say begin transaction, end transaction. And if anything goes wrong in the middle of that transaction, the JCRE will basically go call it off and then be able to roll back to what the values were before the transaction started. Very handy. Yeah. So then there's this idea of a firewall. In No Virginia, this is not the firewall down the road. This is an idea that prevents basically applets from speaking directly to each other. In standard Java, applets can interact with each other pretty easily. Here, you actually have to explicitly state, I'm creating this thing called a shared interface object, and I'm going to allow this other applet to access it. And you have to be very explicit. This is not something you accidentally create a hole in this firewall, unlike, say, running checkpoint on your corporate network, which accidentally there are holes in all the time. This is something that it's fairly complicated. You should really think through. One of the dangers with opening holes, besides the obvious of allowing another applet to interface with your applet, is this idea of transitivity issues. If you open up and expose a hole in your applet, and then your applet is accessing somebody else's applet through one of their SIOs, potentially this first applet can come in, do something bad to you, which causes it to trickle down over here to this third applet. It's an odd situation, but it does occur. So when you're creating these SIOs, you need to be very careful that you're not opening up more holes than you actually anticipated. And exception handling is handled by the JCRE, and this is really key. Smart card work, and by work I mean trying to break them, is all about trying to get the card to do something that it's not supposed to do. Exception handling is obviously detecting when the card is doing something or the applet is doing something it's not supposed to do. If you're not paying attention to your exception handling, you can get the card into interesting situations. You can get your applet into interesting situations, which will allow an attacker to do something they're not allowed to do. So you need to be very cognizant of where things are going to go wrong. You need to catch exceptions, you need to throw them, and you need to protect yourself. You need to recognize when you're writing a Java card applet, when you're entering a hostile environment, and when something's going wrong, it's time to lock down. Find a way to protect yourself further. Java card security, so in a nutshell, you've got type safety, this whole idea of off-card verification, malicious bytecode. So here's this deal. You write this cat file to disk, and it's Java bytecode, and it gets loaded onto the card and instantiated as an applet on the card. If an attacker is able to modify that bytecode, in the Java card architecture, you have no way of detecting it. You can even put in, sir.
Since you said they were like jar files, is there a mechanism like jar signer to sign jar files and cat files?
There are various specifications that define signing mechanisms. It's not something that's native to Java card, but it's something that you can implement yourself. There's obviously the crypto capability, or you can get a card that adheres to some higher order spec. I'll get into one in a minute called Global Platform that basically gives you this mechanism natively. You can modify bytecode to put in non-proper, bytecode, things you normally wouldn't see in Java land. Once all the bytecode verification's been done, you can basically go in and scramble the whole thing up. And the card manufacturers generally don't anticipate that occurring. So really nasty stuff can happen to this card when suddenly you're just shoving in random bytecodes. It gets ugly, and generally the cards become doorstops when you do this. They'll actually just completely cease to exist, but sometimes interesting things do occur. So really you need some other mechanism to help you out, as Don got into. So here's some scenarios. A credit card vendor gives you a smart card, and it allows you to load applets after the card's been issued to you. So, maybe someone else loads a malicious applet onto the card, and it attacks other applets on the card, or attacks the card itself. As much as they try to protect things, you can still wreak havoc if you're really trying by loading a malicious applet. Maybe there's a malicious terminal that just terminates the wallet applet. I've got a loyalty application from Hertz Rent-A-Car, and I go to Avis, and when I plug my card into the Avis terminal, it says, you know what, you shouldn't rent from Hertz anymore, and it just kills the applet. Obviously, that's not a good thing to have happen. And a legitimate terminal could be subverted to load malicious bytecode. In the stock Java card land, these are all real possibilities. Again, this just starts to reek of, well, you obviously need a lot more to do to protect the card. So, global platform. Global platform originally was open platform, or open platform was originally global platform, whatever. It's created by Visa, and obviously then it kind of revolves around the financial industry, but it provides a really solid framework for controlling code loading onto the card, and even interaction with the card. It provides a per apto MAC, basically a cryptographic checksum. Think of it as signing each packet that goes to the card, that goes back to a key that's either some shared secret key with a card in the terminal, or some kind of public key cryptography that says, yes, this apto was sent by someone I trust, and by trust means I have the key. It also allows you to encrypt the apto itself, so even people sitting in the middle of the transaction aren't able to determine what's actually going on. It allows you to have a cryptographically signed cap file, so you can go in and say, well, unless this cap file was signed by a key that I trust, I'm not going to allow the code to be loaded. And it gets a little more mundane than that even. It allows for the cap file to contain multiple applets to be signed by different application vendors, and it gets nonsensical after a while. There are no vendors that implement global platform completely yet. However, there are a lot of vendors who are starting to get it figured out and at least have the macking and the encryption put together, and are really able to effectively control the loading of cards, or loading of code on the cards. If you get a global platform card right now, you will likely not be able to just shove an applet on it without the key. They're pretty damn good. Global platform, in my opinion, if you see vendors going to a more open card in the future, which really does allow Hertz or Avis or whoever to load applets after it's been issued, they'll likely be using global platform. I've been kind of in the global platform world for a couple of years now, and I'm really impressed with it, and I think there's a lot of future here. However, it also is very complicated, and the smart card vendors are still just getting it figured out. I've used these terms. This slide is obviously woefully misplaced. Pre-issuance, this is the idea of issuing a card. And issuing the card means it goes from the card issuer, like Amex, to you, to your hands, or goes into an envelope and goes through the mail. In pre-issuance, which is really a state in Java card, the card is assumed physically secure. This is this idea of the cap file, not getting modified because you trust the card, you trust the terminal, you trust the application provider, all this crap. Post-issuance is when it goes downhill. Once the card actually gets in your hands, that's when most of the models that they use for attacks decide, well, this is where we need to pay attention. And so a Java card, you can actually say, all right, you've been issued now. The card is effectively in the field, and now you need to do a little bit more to protect yourself. So from a Java card perspective, the biggest thing that means is you can no longer declare native methods. And a native method is one that's basically, it's not Java anymore, it's interacting directly with the microcontroller on the chip. So you're able to go in and just issue effectively assembly code inside of a pre-issuance applet and put it on the card and do whatever the hell you want to do to that. I mean, at that point, you're just under the radar of Java. That's a really bad thing to have happen in the field, so they disable that ability once you actually issue the card. So in Java card, there's some methods that I'm going to go over. I'm not a developer by trade. I'm getting up here and ranting about software issues, and that's because the company I work for right now does a lot of software work, so I've got a bit of that indoctrination going on. I write really bad code. I'm not a good hacker. I'm a good defender, and I can run networks. And I've actually been forbidden from writing code at jobs before, because after the first Applet application I wrote, they said, no, never again. You go sit over there, we'll write the code for you. So I'm going to talk about this stuff. If you ask me questions, I will likely not know the answer. So there's the biggest caveat on the planet. So the install method is called, shockingly, when you install the applet on the card, this instantiates the applet, which effectively any objects that weren't initialized by the JVM for whatever reason are initialized at this point. It allows you to do some extra foo to basically get your applet ready. You can do key creation and nonsense like that. And you have to call this register method. So the JCRE, basically, it's got a little registry that it keeps track of what applets are on the card and what state they're in. And if you don't call register, it actually doesn't register you in the registry. Sir? This is whenever you're loading an applet. So the applet can be loaded post-issuance or pre-issuance. So this registry, if you don't call register, then the card doesn't know you're there, and your applet is effectively just taking up space, and you have to go in and delete it. So if you're developing these things, don't forget to do that. So select is what gets called by the JCRE once it's got an app due, and it said, everything's okay, I'm going to pass this on to the application. Backpedal. When the JCRE gets a select app due, the select app due is basically, every application has a name or AID associated with it. And when you want to interact with an applet, you have to select that AID first. So when you issue a select app due, first the Java card virtual machine will basically do anything it needs to do to verify what's happening, and then it punts it off to you and says, someone's trying to select you. And you may want to do things like, basically just kind of get the ball rolling to prepare for the next command that's going to come down the pipe. So this is your notification as an applet that, hey, you're ready to rock and roll. Now you got to start thinking about processing packets. Conversely, when someone deselects you, and they don't actually explicitly deselect you, they just select another applet, your deselect method gets called before their select method. Sounds like a fun time for denial of service, right? You just put your deselect method into an infinite loop, and then it never goes away. Fact of the matter is, the JCRE specifies, look, I'm going to call your deselect method, but I'm in no means going to give you any time to do anything. So you got, about a microsecond to think about it, and then I'm going over to the other guy. So this deselect is a non-blocking process. The JCRE will just step right over the top of you if you take too long in your deselect. And then the real one, the real method you got to be concerned about is a process method. Once you've been selected, any app due that comes to you after that will go to your process method. And this is where you get handed an app due, and this is where you do your real work. So if you decide, hey, I'm going to be storing this, mad crypto or whatever the hell I'm going to do, then it gets to your process. You got to parse it. Usually ends up in this big case statement, blah blah blah, and here's all your app dues. So here's what it looks like. This is what I mean by smart cards not being exciting. I mean, you think looking at network dumps are boring. My God. I've seen screens just full of this stuff. And after a while, it's like the Matrix. I mean, you can just kind of understand what's happening, but it really, to the layman, it's the most boring. I've given presentations on smart cards and get to the demo screen, and eyes just glaze over. That's why there's no live demo. This is like the closest you're going to get to a smart card today. Basically, the first app due, I want to power on the card's powered on, and I want to select AID 1, 2, 3, 4, 5, 6, 7, 8. This is a global platform card, so I'm specifying 80 for a class, which is basically non-encrypted, 50, which is select, and then I'm not passing any P1 and P2 to it. The next one, 8, says I'm passing you 8 bytes, and then 1, 2, 3, 4, 5, 6, 7, 8. So this is select that applet. The card replies back with 61 1C. 61 means I have some data for you, and I have 1C of it. So why don't you ask for it? The next app due is me saying, okay, here's 00, which basically is an ISO class, C0, which is give me something, and then 1C, which is the give me 27 bytes of the stuff. And then the card replies back with blah, 27 bytes, and at the end you'll see a 9000, which in global platform land means everything's okay. That's an exit code 0. Just keep on trucking. So, yeah, secure coding isn't complicated enough. Let's get it into a smart card. It's actually kind of shocking. Java card itself and writing the applet that sits on the card is not the hard part, it turns out. it's usually the stuff off card that breaks the whole system. You can write a bad applet, and you can definitely do things to screw it up, but take into account all your other secure coding practices that you have in your enterprise, because we all have them, and all our software engineers adhere to them, right? And then give them some more and say, this is what you need to do when you write the applet. Some manner of code signing. I don't care if you homebrew the damn thing. Don't field the thing if you're just going to allow anybody to put any applet they want in your card, because you might as well not do it and just hire a bunch of guards to do whatever the hell it is you're trying to get the cards to do. A big thing to be concerned about is velocity checking. Velocity checking is this idea of how many times has something happened in the last X number of minutes, and am I going to allow it to happen again? So the typical sin flood kind of idea of, oh, I've seen a lot of sins from you, I'm just kind of ignoring you for a while. The problem with a smart card is time has no meaning. The card, when it's powered off, doesn't know if it gets powered back on 5 seconds later or 5 years later. It really has no clue. So velocity checking in smart card sense is really just this idea of going through and seeing how many failed somethings you have, and just period. You don't care how long or what's occurred between them. You just care that there's been a bunch of failures and nothing successful for whatever this action is that you're velocity checking. For instance, the big one is pin failures. If you see 4 or 5 pin failures, you should probably do something to protect the card. Usually you have a pin for the user, and then you might have an administrative pin that only the people who issue or maintain the card systems are aware of. So if the user fails his pin 4 times, then you'll lock it, and they have to take it to the administrator, and the administrator has to enter in the right pin to then unlock the user pin. And if the administrator fails 4 times, then you should just shoot the card in the foot. You should terminate everything and say, hey, sorry guys, you're going to have to get a new card because I'm likely trying to get hacked. And really this idea of velocity checking is something you need to go through as you're writing these applets and say, what's sensitive? What do I need to watch for? Where can someone get information about me they shouldn't have? Another good one is random numbers. These things all have RNGs on them, or PRNGs, and they may be good, they may be bad. And as an attacker, I may be interested in just harvesting random data in an attempt to find some statistical weakness in your random number generation. So if you see someone doing an activity that generates a lot of random data, kill it. Just kill the card. Only share what you need to. This is obviously least privilege, best practice kind of concept. I know it should go without saying, but how many people in the room write software for a living? Okay, I will not make disparaging remarks about software developers the rest of tonight. I've had a lot of bad experience with software engineers who, unfortunately, just really don't quite get security, and by get I mean care. I like the ones who are willing to listen, but the ones who aren't generally just want to drop kick. And this even gets into architecture issues. This gets into requirements issues. You need to watch what you're sharing. You need to watch what the card's going to tell people. You need to watch what the card in the applet is going to tell other applets. Proper exception handling. Yeah, I've done that. Transient data. So here's the transaction methods. Note there's also an abort transaction. So you yourself can detect when something's gone wrong in the case of a transaction. The Java card runtime environment will detect it anyway. If something like if you just pull power, if you just pull the card, it's called a tear. If you tear the card from the reader during a transaction, the JCRE will recognize it the next time you put it in, and it'll clean up that transaction. However, you can say this transaction hasn't gone the way I expected it to, abort, and then JCRE will roll back for you, and the card's still powered on. A note about tearing smart cards. That term is used all the time to describe basically pulling power from the card, and it elicits this idea of a very physical, guy sitting there. He's got the stopwatch, and he rips the thing out, 2 microseconds late. Tearing from a sophisticated attack standpoint is not done by hand. This is something that will be controlled by a computer, where you are watching the power draw. You'll issue a command, and you'll see things happening, and you get to a point you say, when I see this, I want to kill it. I want to pull power. And you time it, you set a timer, and you say, I issue, and then I pull. That's what happens. That's what a real tear is. Tears in the field are bad, like someone just pulls the card out and oh, damn, now I got to clean up the mess. But in general, the card's going to recover from that. It's a real well-timed tear that you need to be careful of. Things are smaller on a smart card. You can't put a hell of a lot of logic in there. You can shove a lot in, a lot more than you would expect. The average smart card applet is going to be between 2 and 3K. It's not the most massive thing, But if you're not paying attention, you can suck up 8 or 9K in a hurry and get yourself backed into a corner. Keep it small, and remember, what's transient, what's persistent, what parts of memory you're creating, because if you keep instantiating new objects every time, like I just keep creating this variable, new every time, it's actually going to end up getting written into persistent EEPROM memory. And you're just going to suck up all your memory after you use the card enough times. If you've got something that you really want to declare new, you have to declare it transient as well, so basically it gets destroyed every time the power is torn from the card. And really, when you're designing the protocol, be the bad guy. I've gone over a lot of this, but I can't overstate the number of times this has happened in the industry. If you go to Google after this, because the power of the smart card compels you to go learn more about it, and you decide to look up smart card security, the first Google of answers you get will be like hacking DirecTV. DirecTV is all about smart cards, and that's how they control access. And there's a giant market, multi-million-dollar market around creating fake smart cards for DirecTV. And this whole cottage industry of making these little things that will write these cards for you and allow you to make money at home. That's how you make money at home, right? You make smart cards for DirecTV and sell them to people in Brazil. You're going to have to dive a little bit deeper if you go searching, but nonetheless, that's an example of things have gone wrong. They fielded millions and millions and millions of these cards, and now they got to figure out a way to take this fielded system and make it secure, while it's still going and without recalling everything. It would be pretty impossible for DirecTV to go out and recall all its receivers right now. I mean, it's damn impossible. And they've done a lot in their to be fair to them, they've done a lot to try and combat this. I'm sure a lot of you were familiar with this idea that they had a few years ago where they were slowly, they can download things in these smart cards. And people watch what they would download, and they have little things that would block it, basically, to prevent them from downloading this code, because the code was generally going in and trying to destroy these fake cards. And so then they made it say, well, you had to be able to write it, or if I don't detect the write, then I'm not going to allow you to do it anymore. So the people had to pull out these little terminators that disallowed them from writing, and so they were dropping this code in. And they're dropping in a few bytes a day, here, there, pow, 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 la, 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 and everyone's kind of going, I wonder what they're doing. And then one day they dropped in the last byte, and then they activated it. And it was basically this program that they dropped in over the course of like 6 months or a year onto all these people's cards, and as soon as they activated it, just poof, terminated them. And so they'd all been watching like kids at the zoo, like, wow, what are the elephants doing? Oh my God. So they're doing a lot, but you don't want to have to do that. I mean, you really don't want to have to field these systems and then recall everything or screw around with it for years to try to avoid an attacker. Granted, for a lot of people, what's at risk isn't quite that large, but nonetheless, it's your company, it's your product, it's whatever it is you're doing. You got to pay attention to the details. Decompose the protocol, figure out where the vulnerabilities are, and fix them. Cryptographically sign anything sensitive that's occurring. And there's all manner of prior art out there about things that have gone wrong. And in general, some of the write-ups about how they've been broken, like this Blackboard thing, the DirecTV, GSM stuff is starting to get a hell of a beating lately. There's a lot of technical breakdown of what's gone wrong. This is the good part of full disclosure, right? It's not giving the hackers more ammunition. It's allowing people like us to go out into the field and say, well, I'm going to do the same thing. I'm going to learn from history. I'm going to go out and I'm going to do this right. So, few odds and ends. If you're going to do this, I recommend using the Muscle Project, which is the greatest acronym known to mankind, and you can find it at linuxnet.com. This is an open source implementation of PCSC, which is the Personal Computer Smart Card specification, which basically provides a pretty coherent way of PCs to communicate to smart cards via a serially connected reader. Microsoft has a PCSC implementation that I think is an XP. I mean, that's pretty much what they're using. They're not using this code. Well, maybe they are. But this is the spec that they've coded to. There's a lot of code there. I mean, there's an awful lot of code there, and you can get that stuff and you can tear it apart. It's well documented. They've been doing it for years. There's OS 10 support. I'm a big OS 10 zealot. So if you're OS 10, you can download it as well, and you can start to play around with it. Sun, obviously, as the proprietor of Java, has oodles of documentation on this, although it's kind of hard to find at times. There's a really good book called Java Card Technology for Smart Cards. It gives you a lot of examples of how to write applets. They don't really talk about applet security that much, but I think you can kind of extrapolate based on secure coding guidelines that I've given you here and the things available on the net, what you need to do to write a good application. Card vendors, Obithur, Gemplus, Schlumberger are kind of the biggies. Gemplus has a nice online store. You can go buy this dev kit. I think it's like $200. It comes with a reader, 5 cards, CDs, a code, all this crap. It's really pretty slick. Schlumberger has kind of similar deal. Gemplus's site was actually, like their store was down for maintenance when I tried to check their prices, so I can't recall all the odds and ends of what they cost. But it was about $200. Schlumberger's $50-ish for readers and about $12 a card when you buy them in lots of 5. And one nice thing about the Schlumberger cards is they actually make cards now with USB logic in them. So rather than have to have like an actual terminal attached to your card, you can effectively take a USB dongle that's just got pins on the end of it that talk USB to the card, and then the card is able to then kind of extrapolate that into its own smart card language and do its thing. So it's like a dumb serial reader, except now they make them for USB. They're real slick, and they're about the same price. And for a deployment in a mid-sized organization, they can reduce your hardware costs substantially. So I highly recommend looking at their gear. I think Gemplus is following suit. They've got something similar. It's a really slick solution. Quick plug, I helped out with a couple of books. They're out there if you want to buy them. I highly recommend it. Any questions? Groovy. Oh, hey. The question is, how much time spent on security testing of smart card hardware versus smart card software? It's really done by 2 different animals, it turns out. The people who do smart card hardware testing are either the smart card creator themselves or third parties who have been contracted to do that kind of testing. For application creators, for software developers, they kind of assume everything's okay. And I don't know that I could put a real hard percentage. A lot of people don't pay a lot of attention to the security of their software, but in turn, I don't think a lot of people pay attention to the security of the smart cards very much anymore because they've overcome a lot of hurdles recently. Smart card hardware testing is a blast if you have the gear. And if you do have access to a college EE lab, I highly recommend going in and playing with this stuff. Paul Kocher's work lays it all out. If you read Paul Kocher's work and Anderson and Kuhn's work, you're an armed terrorist at that point. I mean, you can go in that lab and you can go bananas finding out stuff about this card. And if you take a simple system, you'll likely be able to break it. If you take something more advanced, you'll learn something about it, but you'll likely not be able to do anything interesting. Other questions? Mm-hmm. That would be something that you would load pre-issuance. So while the card's in a protected state, you would go in and load in the keys. And Java Card, obviously, it gives you an API to basically load the crypto keys on. With Global Platform, they provide their own Java-based API to interface with their key handling material. Because of the number of actors involved in Global Platform. You got the issuer, the application creator, you, everybody else on the planet. There's a lot of different keys floating around. So in order to load a key, there's a key encryption key, there's a macking key, an encryption key, there's all kinds of nonsense. So in that case, it gets pretty complicated. But for your own homebrew stuff, you can just use standard issue Java Card X crypto stuff. Fire. Not necessarily. For each system that's deployed, people will generally, say, I'm going to have this AID. Like for Global Platform, the card manager, there's this entity called the card manager, has the same AID on every card. And, in that case, Hertz or whoever would go and register an AID with Visa or someone. But it's not globally unique like a MAC address is. It's something that, if you're just doing this yourself, you could just choose anything out of the air. Something about the select API that's important to know is you can have an AID called 123, and then you can have another one called 1234. And when you issue a select, you can issue a select that matches explicitly a string, or you can have one that matches, that string and then some other stuff. And so you may have, inadvertently, when you go to select your applet, you can tell select, if you tell it just to pick one, it'll pick the first one, and then the second one, and then the first one, and then the second one. There are times when you select yourself, if I went through this select and deselect idea. If you select yourself, what happens is JCRE will call your deselect method, and then it turns around and calls your select method. So it's not a no-op. Selecting yourself in Java card is not a no-op. It actually causes yourself to be deselected and then reselected. But if you're 1, 2, 3, and you do a select for just basically that string plus something else, and you try to reselect yourself, it'll actually go to that 1, 2, 3, 4 AID. And then you're off in la la land. That thing could do anything it wants. So when you're running select, don't get lazy. Know the whole name of the thing and select it by explicit name. Any other questions? Groovy. Hope we all have fun tonight. Stay safe. See you tomorrow.